Hey guys, welcome to your chapter 11 study guide tutorial video, page 1. For this first section, the evaluate each expression. Remember this first chunk of questions that we're going to get through number like 27, I believe. This is all practice for the non-calculator portion. So you need to be able to do these things with just the small calculator. So when you're evaluating, you have to remember all of your exponent rules. And of course, there are a variety of them. So we will kind of hit on each of those rules depending on what is required of the example. So number 1, I've got 1/4 to the negative second power. Well, you've got to remember that negative exponents can be changed to positive if we put our number in the opposite part of the fraction. So like 1/4 is to be considered in the numerator. So if I want to make it a positive second power, I would put 1/4 in the denominator, and with it being squared, and that's going to equal 1 over 1/4 squared is like 1/4 times 1/4, right? Then we multiply fractions straight across, so then this would equal 1 over 1/16. And then 1 divided by 1/16, anytime you have 1 over something, that means take the reciprocal of that number. The reciprocal of 1 over 16 is 16. Number 2, 2 to the negative first power divided by 2 to the negative fourth. The rule here is that if you have numbers with the same base, then we are allowed to subtract their exponents. So this would be equivalent to 2 to the negative first minus negative 4. So you got to be careful with this double negative here. -1 minus -4. When we subtract that, we get 2. -1, that's going to change to plus a positive 4, which is going to be 3. And then 2 cubed is 8. Okay, number 3. Some people might be tempted to take this 1/3 power and distribute it into each of these terms. But please, please, please do not do that. There's no math rule that says that you can do that. You can only distribute terms in like this if your terms on the inside are being multiplied times each other. That's what the rule is. Okay, so instead, let's actually just go ahead and compute these values and simplify using order of operations, PEMDAS, from the inside out. So what you need to remember, anytime you have a rational exponent, and a rational exponent is just a fractional exponent. So a rational exponent. Its numerator stands for the power, and the denominator stands for the root. So hopefully by now you know something to the 1/2 power is the square root, because 1 is the power and 2 is the root. So instead of 16 to the 1/2 power, you can rewrite that as the square root of 16 to the first power, but again, you don't have to write 1. And then similarly with 1/3, if that's power over root, that's going to be the cubed root of 64, all raised to the 1/3 power. And then let's actually get these values. The square root of 16 we know is 4. And then the cubed root of 64, what number times itself? 3 times gets you 64. Again, you're going to have the small calculator, so you might have to do some trial and errors if you're not comfortable with your cubic numbers, and that's okay. Eventually you would find that 4 times 4 times 4 is 64. And then all of that to the 1/3 power. 4 plus 4 is 8. 8 to the 1/3 power is the same thing as taking the cubed root of 8, which is going to be 2, because 2 times 2 times 2 gets you back to number 8. Number 4, -8 to the 1/3 power divided by 8. So again, I'm going to kind of rewrite this 1/3 power as a cubed root. So that'll be negative cubed root of 8 to the first power, but I don't need to write that, right? Power is 1, root is 3, so cubed root of 8, all divided by 8. And that's going to equal negative. The cubed root of 8, as we just did on the last problem, is 2. And then still just over 8. And negative 2 over 8 reduces to be negative 1/4. Number 5, the square root of 15 times the square root of 60. Rules for radicals is that if you're multiplying them, then you can multiply the numbers on the inside as well. So the square root of 15 times the square root of 60. 15 times 60 is 900. And then hopefully that number rings a bell. If not, you can guess and check if you need to. Go in the opposite way. Try numbers like, obviously, 10 times 10 is 100. So it's going to be bigger than that. Specifically, this is going to be 30. The square root of 900 is 30 because 30 times 30 gets us back to 900. Now, I also want to be clear that we're being concerned with the positive values. So even though we know that negative 30 times negative 30 gets you back to 900, we're assuming because there's a positive symbol in front of this that we're going to be giving you positive answers. Number 6 is similar to number 3. So we can rewrite 9 to the 1/2 power as the square root of 9 plus 1 to the 1/3 power. You can rewrite that as a cube root if you want to, guys, but 1 raised to any power is just 1. All to the negative 1/2 power. So then the square root of 9 is 3. So we got 3 plus 1 to the negative 1/2 power. 3 plus 1 is 4. And then we have 4 to the negative 1/2 power. Well, again, when you have a negative exponent, you can rewrite it as a positive exponent if you put that number in the opposite location of the fraction. So 4 to the negative 1/2 is the same thing as 1 over 4 to the positive 1/2 power. And then 4 to the 1/2 power is the same thing as the square root of 4, which is 2. And since that's on the denominator, your final answer would be 1 over 2 1/2. Number 7 and 8, the directions don't ask you to evaluate. It just says express using rational exponents. So it doesn't even really want you to simplify. It just wants you to rewrite these radical forms into exponential form. So again, if you keep in mind your rational exponent is equal to the power over the root, then you take each one of your terms on the inside and you write it with its power over the root is 4. So this will be 3 to the power of 3. There's none written, which is implied that it's going to be 1. So that'll be 3 to the 1/4 power times x to its power is also 1. It's not written, so it's understood. Times y to its power is 4, and the root is 4. Now, I'd probably give you credit if you left it like this because that's expressing it using rational exponents. But it also wouldn't hurt to go one step further to reduce your rational exponents. That'd be 3 to the 1/4 times x to the 1/4 times y. 4 over 4 is 1. So that would be just times y. And I guess technically you'd put square root symbols around that as well, or absolute value symbols, but again, that's just using rational exponents and not really simplifying. So we won't worry about those absolute value bars until we get to the simplify problems. Number 8, same thing, power over root 64. Its power is understood 1 to the 1/3 power. S to its power is 9 over root 3. Times t to the 15 over root 3. And then 64 to the 1/3 power, again, you have to be kind of familiar with these numbers. That's the cubed root of 64, which by now, hopefully you know that that is 4. And then you can reduce these other fractions. This will be s to the 9 divided by 3 is 3. And then t to the 15 divided by 3 is 5. So that'll be 4s cubed t to the 5th power. And then number 9 and 10 go backwards. I give you these exponents, I ask you to go back into radical form. So what I would do for number 9 is, even though you could go ahead and put each of these numbers in a radical, the more you can consolidate your numbers, the better. Kind of like over here how we simplified things. That's what we want to do. So again, we can kind of use our exponent rules. We have two numbers with a base of 2, which means when we're dividing numbers with the same base, we can subtract their exponents. So this would be equivalent to 2 to the 2/3 minus 1/3 power. Well, 2/3 minus 1/3 is just 1/3. And then 2 to the 1/3 power expressed as a radical. Remember, the numerator is power The denominator is root. So I can express this as the cubed root of 2 to the first power. But again, you don't have to write that 1. It's understood there. So the cube root of 2. Number 10, n cubed times m to the 9th, all raised to the 1/2 power. So you have a couple different choices. You can go ahead and distribute this 1/2 n to each of those numbers. Or expressing this as a radical, just do this outside rational exponent as the radical with 1 as the power and 2 as the root. If you do that, then this could be rewritten as the square root of n cubed times m to the 9th power. And that's that. That's as far as you need to go. Okay, numbers 11 through 16 are all about, well, 11 through 14, I'll say, are all about simplifying. Okay, so we're going to incorporate our evaluation rules, but these also have variables in it that we need to consider. So for number 11, you have 5n cubed quantity squared. The thing to remember here is that that squared term applies to both numbers on the inside. It applies to 5 and to n cubed. So this is going to end up being 5 squared times n to the, when we multiply 3 times 2, will be the 6th power. So 5 squared times n to the 6 times n to the negative 6. Okay, well 5 squared is 25. And the rules when you are multiplying numbers that have the same base, we can add their exponents. So we'll have 25 n to the 6 plus negative 6 power. Well, 6 plus negative 6 is 0. So then you have 25 times n to the 0 power. Any number to the 0 power is 1. So then you have 25 times 1, which just simplifies to be 25. Number 12, I've got the square root of something times the square root of something else. And when you multiply radicals, the rule is that we can multiply all the stuff that's on the inside. And again, when you're multiplying numbers with the same base, the rule is that we add their exponents. So this will be x squared times x cubed. 2 plus 3 is 5, so that'll be x to the 5th. Y cubed times y to the 4th. 3 plus 4 is 7, so that'll be y to the 7th power. Now, you actually need to simplify. So you need to, anytime you have a square root or a cube root or something, you need to make sure you take out as any square factors that you possibly have. Now, in order for an exponent to be considered or a number that has an exponent to be considered square, exponent must be even. Must be even to be a square number. Exponent must be even. And the reason for that is simple, guys. If I have the square root of x to the 10th power, the question is what number times itself gives you x to the 10th? Well, that would be x to the 5th times x to the 5th, because 5 plus 5 is 10. So essentially what you do in order to find the square root of a number raised to an even power is you just divide that even power divided by 2. So 5 and 7 aren't divisible by 2. They're not even. So I'm going to break those numbers up into the number just below them that is even. So instead of x to the 5th, I'm going to break that up as x to the 4th times x. And similarly with y, that'll be y to the 6th times y. And then when I actually take the square root of these numbers, I'm going to bring them to the outside of the radical. The square root of x to the 4th power is the absolute value of x squared. You divide 4 by 2, which is 2. Same thing, divide 6 divided by 2, which is 3. So that'll be times the absolute value of y cubed. And then you're going to leave the other x and y inside of the radical. Now let's talk about those absolute values here for a minute. Remember, we don't know, when you have the square root of something, there's a positive and a negative answer. So since we don't know if x and y are plus or minus, we have no idea of telling when we take them out if they're going to negate one another when they're on the outside. So instead of putting plus and minus symbols in front of things, the way to ensure that we're giving a true value of this expression is to put the absolute value bars to claim that we're discussing only the positive answers of that. Okay, so in short, on your test, you're going to put the absolute value when you take numbers out of, and by numbers, let me say when you take variables out of an even root, which is a square root, a fourth root, a sixth root, any even number that would be on the outside, you put your absolute value bars on. So since we took out this x squared and y cubed variables from outside the radical, we put absolute value bars on them. Okay, number 13, p to the 6a power divided by p to the negative 3a power, all to the 1/3 power. So again, you have some choices. We know rules. Anytime you have a power to a power, it applies, in a fraction like this, it applies to both of those exponents, and you could multiply those two together if you'd like. You could take the route that I'm going to take, which is that when you divide numbers that have the same base, you subtract their exponents. So this is going to be equivalent to p to the 6a minus the bottom exponent, negative 3a. And again, you just got to be careful with that minus a negative. And then all of that's going to be to the 1/3 power. So this will be p to the 6a minus negative 3a. It's going to be plus a positive 9a. And all of that's to the 1/3 power. And then the rule when you have a power to a power is you multiply that in to your exponent. So that'll be p to the 9a times 1/3. If this is technically 9a over 1, any numbers over 1, you multiply fractions numerator with numerator, denominator with denominator. So this would be 9a over 3. And then, of course, 9 divided by 3 is 3. So this will just be p to the 3a power. Number 14, 7x to the 6th, y to the 4th, all to the 1/2 power. Again, you can distribute this 1/2 power into every term if you'd like. I recommend you taking or rewriting it as the square root of all of that stuff. 7x to the 6th, y to the 4th. Okay, when you take the square root of this, 7 is not a square number, so it's going to have to stay in the radical, but x to the 6 is. So 6 divided by 2 is 3. Again, I have an even root, which means I need to use the absolute value bars. So this is going to be the absolute value of x cubed. The square root of y to the 4th is going to be the absolute value of y squared. And then we leave the square root of 7 on the inside like this. Number 15, write 3 to the negative 4th power equals 1 over 81 in logarithmic form. So the thing you need to remember here is how to switch from logarithmic to exponential. Basically, your logarithmic form, if I have log base b, actually let me go backwards. If I have b to the, and I don't remember which variables I used in your notes, so I apologize if these are different. But if I have b to the x power is equal to a, then it is interchangeable with logarithmic form. So this would be exponential, which would be log base b of a is equal to x. Okay, so logarithmic form will have this organization if this is your exponent. So if this exponential is b to the x power equals a, when I write this in logarithmic form, the key, guys, is that your base is the same. So your base of the exponent is the bigger number. Your base of the log is the small subscript. So this would be the log base 3 of a, which is 1 over 81, is equal to the exponent x, which is negative 4. So that's logarithmic form. And then, of course, if I give you logarithmic form and I ask you to go backwards, then it would be your base 3 to the negative 4th power equals 1 over 81. Number 16, evaluate the log base 9 of 1 over 81. I'm asking you what value is equivalent to this. So if I set this equal to x, and then again I use my logarithmic and exponential switcheroo over here, if I write that as in exponential form, my base is 9, So that would be 9 to the x power equals 1 over 81. And hopefully you recognize the correlation of 81. 9 squared is positive, which is a whole number of 81. So it's not squared, but 9 to the negative second power is 1 over 81. So that's how we know that x should be negative 2. Because we would take the reciprocal of that number and make it a positive exponent. For 17 through, and this is going to go on the next page, even though the next page is going to start the next video. 17 through 20 are all about graphing these exponential functions. Again, I ask you to make a table of 3 values, determine the horizontal asymptote, domain, and range, both in interval notation, and then graph it. Now, you don't have to make the chart the way that I'm going to show you, or the way that we learned, though I do think it is the easier way. You of course, can just generate a table any way that you know how, but being mindful that you can't use the graphing calculator. So if you follow my lead with the table, the thing you have to remember is that these equations are of the form y equals a times b to the x minus h power plus k. Okay, so we can identify our variables in terms of their position. So for your table, you always start your table with x, which you get to choose what values of x you want, and then you do b to the x power. And then, after you start there, you continue on the expansion of your x variables by adding h, and then you go ahead and keep changing your y coordinates by first multiplying times a, and then adding k. So this is how you create your table. For this question specifically, let me make these a little shorter. For this question specifically, let's plug in our variables. Now, x is always x no matter what. B to the x power, b is the base of your exponent. That's just 1/2. So this would be 1/2 to the x power. And I'm going to take care of these first. For x's, I recommend you choose -1, 0, and 1. Life's just easier that way. Then when you plug in, you're going to plug them into 1/2 to the x. So if I have 1/2 to the negative first power, if I want to make this a positive exponent, that's going to be 1 over 1/2 to the positive 1, which anything to the first power is just itself. And then 1 over 1/2 is 2. Okay, the next number, 0, 1/2 to the 0 power, anything to the 0 power is 1. And then 1/2 to the first power is just itself. So a couple of tips and tricks. Every single time that you start off this table, if you choose -1, 0, and 1, your middle coordinates will always be 0 and 1, because anything to the 0 power is always 1. Additionally, the other two numbers will be reciprocals of each other every single time. And then from here, I like to go ahead and add h. Since we have x minus 1, that actually means h is going to be plus 1. So we're going to add 1 to all of these x values. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. And then we're going to multiply your y values times a. A is -4. That negative is attached to a, so you got to make sure to put that in your table as well. 2 times -4 is -8. 1 times -4 is -4. 1/2 times -4 is -2. And then lastly, plus k. In this example, k is -1. So -8 minus 1 is -9. Then -5. Then -3. So these outside numbers, outermost numbers, are your coordinate points. Those are the numbers that you are going to graph. 0, -9. 1, -5. 2, -3. Now, before I connect these coordinates, I want to go ahead and find my asymptote, because what that's going to do is tell me where my graph has to level off. Now, your asymptote, guys, will always, always, always be denoted by k. So since our k value is -1, then that implies that our asymptote is going to be the line y equals -1. I stress the line because I need you to make sure you give me that equation for the asymptote. It's not just the number or a point, it is the whole line. So go ahead and graph that horizontal line at -1, and then you can go ahead and make your curve. Now, when you give me the domain and the range in interval notation, usually for domain we've just been putting all real numbers, which is true, but in interval notation, I want you to be very specific there. That interval for a domain goes all the way from the left at -infinity up until the right at +infinity. For the range, you've got to remember, and guys, this works for any interval notation. Interval notation. So for any interval notation, you put the smaller number on the left, and then you go up to the bigger number, which is why for domain, it's -infinity to +infinity. For the range, my graph is going down all the way at -infinity, and then it's going to level off at -1. Well, -infinity is smaller than -1, so that's why I've got to put -infinity first. And so these three are the attributes of the graph that I'm looking for. Okay, for number 18, again, we're going to start off with our chart. This time, it's going to start with x, and then b is going to be 1/2 to the x power. So if I start off with -1, 0, and 1, 1/2 to the negative first power, these are actually going to end up being the same numbers. 1/2 to the negative first power is going to be 2. 1/2 to the 0 power is 1, and then 1/2 to the first power is 1/2. And then I'm going to go ahead and add h. Well, if I have x plus 2, that actually means I'm going to subtract 2. I'm moving everything to the left 2. So -1 minus 2 is -3. 0 minus 2 is -2. 1 minus 2 is -1. And then I'm going to multiply times a, which will be times 3, which will be 6, 3, and then 1/2 times 3 is 3/2. And again, guys, if you just think at fractions, then do decimals. These are manageable decimals. You know that 1/2 is 0.5. That's fine. So that would be 1.5. And then lastly, we're going to add k, which would be plus 2. So that'll be 8, 5, and then 4/2 plus 3/2, which will be 7/2, or you could do 3.5. Again, the outermost columns is where we're going to get our coordinate points. -3, 8, -2, 5, and -1, 3.5. The asymptote, horizontal asymptote, will be the equation y equals k is 2, so the horizontal asymptote will be at 2. And then we can go ahead and connect our coordinates. Our domain, it will always be all real numbers, which will span an interval notation from -infinity to +infinity. And then for your range, again, that's my y values. The smallest y value that we're going to go is at 2. And then my range goes all the way up until +infinity.